Thank you very much for the introduction. I would like to thank the organizer for inviting me here. It's a very pleasant place to work. So today I will present another way to construct a two-value p-adic function. So given a modular form satisfies some condition, we know how to construct a p-adic function associated to the p-stabilization of this modular form. And so in this process, in fact, we have different methods which correspond to different realization of motif. So the first method is the method of modular symbols, so which correspond to the Betti cohomology, Betti realization, and we also have the Rankin-Seppelt method, which is the Hahn realization, and then we have the method of Euler system, which is an element in fact in the Galois cohomology of the eta cohomology of actual variety. So simply say they correspond to the eta co-realization. Now we want to deform this form into a p-adic family. So we can deform the different method. So this gives you several ways to construct the two-variable p-adic function. So if we want to deform this over the eigencurve, but there are several methods to construct the eigencurve. So once you deform this, and you may find a different method to construct eigencurve. Then you combine them, it gives you more constructions. Okay. So in this talk, I will talk about the construction of the universal Kato solar system, and then use Hamilton's construction of eigencurve to construct the Kato solar system over the eigencurve, and then apply the nowadays standard technique to get a two-variable p-adic function. So this talk divided into two parts. And as how the two-variable p-adic function. So because the construction from Kato solar system to this two-variable p-adic function nowadays a little bit standard. So you can find so using different methods, but not using universal Kato solar system, but use other construction from Kato solar system from over eigencurve to this one. So you can find in my preprint Kato solar system in family, and you may also find this in Hansen's. I don't know it's preprint or a published paper now. Or so last year also you have Ochia, Filippo. So this from here to here is some kind of standard. You have lots of difference. So in this talk I will talk more on the first step. Okay. So let me fix prime P5 and fix the embedding Theta m always means the mth root primitive, mth root of unity. And let's fix the integral n applying to p. Okay. And we denote y1n, the open modular curve of level gamma 1n. Defined over Q. And later I will just write pi1 Q eta, the eta fundamental group of y1n, and pi1 eta Q bar, the eta fundamental group of y1n base change to Q bar. So first let me record the construction of Kato solar system in the presentation of comets. So we start with Siegel units. So first we place integer prime to 6, and we have this function. Sorry, it's tau z, tau 6z minus 1. And here tau in the polar is a variable in polar upper plane, and z is in C. And this theta is the theta function. So here Q is equal to e to the power 2 pi I tau, and QZ is e to the 2 pi I z. Okay, now this function is an elliptic function on variable z, and it has a period lambda tau. The theta function is not a period, it's not an additive function. And we have a proposition Kato, which describes the property of this function. So this function, this additive function is a unit in the ring of, say, so this is the ring of holomorphic function on and for any a bigger than 1 such that a prime to C, and we have the norm relation, and this norm is defined. So C equal to 0 to a minus 1. And the norm relation tells us is equal to, is invariant under this norm. And so if you choose another integral d satisfies the condition there, and we have have the relation D. So here C star so this is the definition. Now, because it's an elliptic function, now you can think about its function on a universal elliptic curve. Then, if you take the torsion section of the universal elliptic curve over the modular curve, you can pull back to the modular curve. Then, in fact, in this way, you get a Siegel unit. So, we take a lifting of elements in Q square, and we define this G alpha beta equal to, so now it's a variable in tau, G. So these functions we call an Siegel unit. So the following proposition describes the property of Siegel units. Now this n is not the n we fixed at the beginning. We can vary it. And if say prime to 6 and say alpha, say beta not equal to 0, then this G alpha beta is equal belong to the so this is the group of modular unit of level gamma, principal level gamma n, and with the coefficient of Q expansion in the cyclotomy of Q, extension of Q. So in this way, we can pass from the complex to algebraic. And we define G alpha beta. Now this is an element in this U. Yeah. So sorry, here I have C. Right here we have C. So we just so this is a group. We just tensor over Z to Q, and we get this. The vector have this element in this vector space. No, sorry. Yes. So this is G alpha beta defined. And this doesn't depend on choice of C congruence to 1 mod n. And from this element, we can recover G, say G alpha beta for any say. We have this G say alpha beta equal to this G alpha beta say square G say alpha say beta minus 1. Okay. So this for. And we also have the action of G2Z hat on this Siegel unit. So here the action is just the multiplication of matches. And so we just use this as a movism to give a sense for this multiplication. Okay. So they had. And so there's a last property correspond to this invariant under the norm, which is we call it just the distribution relation. So you can just a translation of that the norm relation, and we can summarize all this into the language of algebraic distribution. So there is this Siegel H with value in this vector space. Now this means the good of modular units for all the level, but the coefficient of Q expansion lies in the cyclotomic closure of Q. And so this algebraic distribution satisfies the following condition for. So we take an open. And we have this A plus hat plus. You take the integration, and it's equal to this Siegel unit. Okay. And moreover, this algebraic distribution is fixed by the action of. So this is invariant under I.1 Q eta. So how this S? So we have the following diagram. And here you take the cyclotomic character, goes to Z hat. And here you have a section. Here you have a section by sending D to so D, and this commute. Okay, so pi1 q eta s, in fact, vector through its image integer to z hat. Huh? This D, so you have a, sorry, star, cyclotomic character, yes. So in this way, we have Siegel units with in H0 of this pi1 q eta. And I also need to explain here, algebraic distribution just means the dual of the locally constant function. So now, for simply, I write as, maybe I put here, for notation, x1 equal to AF. Okay. So we have a exact sequence of 1 to QP1 to Z to this U Q bar tensor Q1. And here Z is defined as a sequence of Gn. And here Gn in such that Gn to the power P equal to Gn minus 1. Sorry? So algebraic distribution is just the functional on locally constant function. And as we get is a sequence on algebraic distribution. To this and here we really need to tensor with Q because this space is very huge. If we work with Z modules and then we take the continuous cohomology, then we get some problem. And so here we take here we put the discrete topology here. And here the topology is per finite topology, and here is the p-adic topology. So that we can take the continuous cohomology of the pi1 q eta. So here is the discrete topology, and this one is per finite, and this one is per finite. And because we need this discrete topology to have the section group. So it's Gn maps to G0. QP1 is the kernel of this map. So first we need to prove. In fact, we need to prove this one is surjective. Now we have the Kummer map for this. Of the x1 is u bar and so q to this h1 q eta to qp1. And we have this Siegel. We denote this image, right? Siegel. And then we take two copies of this element. We take the cut product. H2. Yeah. Sorry. Yeah, usually very long note. And we identified. So once we have two copies of this, we identify the AF4 with AF, and we denote this X2 is M2, outside of P is M2AF. At the place P, we put J2ZP. So in fact, we take the cut product and then restrict to this X2, QP2. So this is the Kato. Which map? This map. So you have a sequence of modular units, and you just map the sequence to G0, to the first one. This is yeah. Okay. And now we want to, so this is with value in QP2 is not, we need to modify this element such that it's in ZP. So algebra distribution can extend by continuity to a measure. So we applied, I don't give you the precise operator, but it's an element in CP to say hat. And we apply the operator RCD to this Kato, and we denote it by CD set Kato. And now, so you can get this is with value in ZP, and then the algebra distribution with value in ZP is the same as the value is measured space. Okay. So this is important because we need to change the coefficient here, or go to symmetry power, or go of symmetry K of QP2, or change or twist by this power of determining orientation. We need a measure. So that is the technique. Okay. Now we denote T, the generator of the determined representation of shear to Z hat. Now we have this map from this CP2 to, you just multiply with the function then you get CP1. So this map is I1 Q eta. So you can take the Galois cohomology. So you get this H2 of this pi1 Q eta. D0 CP2 to the same thing CP1. Okay. And we denote the image of this CDZ Kato. Here still Kato C1. Okay. The space of measure space. Yes. Because this is a continual function. If you have algebraic distribution, you can integrate with it. Okay. So now we can construct a universal Kato solar system now. Starting from this element, we can construct a family of elements, say Zm. So this is our M in H1. Iwasawa, Z, theta M, and inverse MP with value in H1, I1 eta Q R, space of measures on shear to ZP close K1N. So K1N is, later I will explain what it is. So K1N is a subgroup of shear to Z hat and acts congruent to star 0, 1 mod n. So it's the adelic level correspond to gamma 1n, but you have different choices. So I choose this one. And K1 and n is just you just take the component at the place divide n. So this is for all m and prime 2 and m square of 3. And for all system, we need the position of this ZML is equal to Zm, and with the action of 1. So this is the Hacker operator, TL. So this is the, this is the, so you put this in the other language and you just take the component outside of L. Plus, so if you look at this relation, once you have once you have a Galois limitation associated to a modular form, this will really give you the correct polynomial. Okay. So to do this, first we choose for any m. We choose this function phi m, locally constant function, and times L divided m, the function 1 plus Lm2 Zl. Okay. So this is a locally constant function fixed by k1n with this k principal km, and it's valuing local constant function with compact support on this. So it's just as L2. And we take the couplet out of this function with our Ct z Kato 1. And we denote this mzm is equal to the integration of this phi m. Now it's the element in H2 of this I.1 eta. But now this one is Q final Zm of the, I denote M here is the level here, and sorry, we just take the integration outside of MP. So we have this place P and the temp place there. So you have this K1n, CP1. Okay. And now we go to this H1 Iwasawa. So maybe it's better to separate in one step. QZM. So we use the so here we can introduce more variable. So this is induced by if you have a continuous function on this CP, cross CP star, and you can map to this continuous function on to CP by setting phi map to x determine. So phi, let me write delta phi x equal to phi x determinant s. So this map induces a map here. This map is also equivalent under this action. Okay. And now we apply this is isomorphic to, this is isomorphic to H1 of this Iwasawa cohomology of this Zm and P, and H1 geometry of level M, and you still have this K1 and CP1. So yes, and bad place. So why I keep the information here is I want to relate this with the complete cohomology of Hamilton. And now the level here is not correct, but we can use the Newton theory to we can project to the space of H1 Iwasawa set H1 I.1 cuba eta, and with the same thing there. So our ZM in fact is the image of this element through this map. And the relation here you can detect from the relation, so you just detect for this Zm, and you have the correlation map for this ZML, and you just by studying the locally constant function will give you the relation there. So this relation can be proved by the follow the construction. Okay, so because here level is higher, so I project to this part. I1 cube, but so this one, now you see here we leave the level. And so this is just the Pi1 geometric fundamental group of the modular curve of that level. Okay. And because this, for all this construction is the same, now we just look at Z1, m equal to 1. Okay. Now we face a residual representation. GQ. Okay, L is a finite extension of QP. So we assume it's modular and such that. So this one is modular and absolutely reducible and also unramified outside of MP, and such that we have some condition on its restriction to GQP. So all these conditions are required in Hamilton's proof of local global compatibility. So here, chi-bar cyclotomy is the more p cyclotomic character. So here is for any chi. Not of the form. One. Okay. Modular. GR2, well. Yeah, sorry. Okay, so now we have, so you restrict to GQP. Not to GQP. I want both of them. Yeah. So this one is yeah, I don't want to say too much. It's some condition comes from the p-adic local line correspondence. Now we have this complete cohomology with compact support, which is defined. So this is definition. So it's just part of the complete cohomology of emitter. So we take this K subgroup of K1n such that K outside of n is equal to P. Yeah. So we fix the other group place Y, K, and ZP. Okay, this is this has an action of GQ and sorry, the compact support GQ and Hecke algebras. So it says spherical Hecke algebra, and you also have the action of G2QP, and you have an action of G sigma with L divide n G2QL. And also representation of G2QP is admissible finite representation. Okay. Now we take for this. We can take localization of this this complete cohomology with respect to the residual representation. Because we assume this is residue, or maybe for simplicity, we can also assume this. It has a modular lifting of the form of level gamma 1n. Then this corresponds to a maximal idea of the Hecke algebra as on this complete cohomology. So we can take the m-adic completion of this Hecke algebra, and in fact it's the summon of this Hecke algebra. And then now we have this, it's just the T. Okay. And our space, well, wait. So our space here, so remember here we have this G2ZP cross K1 and N, ZP1. Now we have a pairing of this one and this complete cohomology. Because if you use Shapiro lemma, you get this H1C of pi 1 Q bar, but with value in continuous function with the same topology space with value in ZP. And you take the pairing and you take the integration on the coefficient, and you get goes to H2 of this pi 1 Q bar eta ZP1. is isomorphic to ZP. So this allows to get a map from to H1 Iwasawa to this H theta 1 C dual. So this is ZP dual. Okay? So this guy is ZP dual. And we have the local global compatibility Hamilton says we have the isomorphism is pi p tensor is pi sigma. So this is over the Hegel algebra. And this is a G to QP representation, and this is the universal. So it's the universal deformation of over this piece. And this pi p is a deformation of pi p bar, which is correspond to this by more p local Laplace correspondence. This is a deformation of this one. And there's a relation between these two. If you apply the Kummer's functor, you get this one twisted by inverse of the cyclotomic character. And this pi sigma is the co-admissible representation of G sigma by the local Laplace in family of Hamilton and Helm. So this is local Laplace correspondence in family. And so this complete tensor product is very important because this one is not admissible binary representation. But if you take the complete tensor product, this will reduce the size of pi p and give you a admissible binary representation. So we have an element here, and we can use this. And this goes to H1 Iwasawa, the same thing, and tensor, complete tensor product over the Hegel algebra, and with this pi p tensor pi sigma dual. Now, one can pass from this is a G to QP representation, and we can take the locally analytic vector, and we can apply the Jacob module of Hamilton, which is a sub of this representation, and we get so this goes to the Jacob module of this. The Jacob module take the ZP dual. So in here it's not ZP dual, now it's QP because you need to take the locally analytic vector, you need to inverse P. So now it's a QP vector space. So let's say. Okay. And so if you have a classical form, in fact, you can do the same thing. And here you also take the Jacob module, and you have the case where you have two refinement, and here you really have two vectors, it's two-dimensional vector space, and you take one vector, and you get the Euler system correspond to the piece visualization forms. And here, in fact, we can, this is just a family version of that idea. Now you can, so Hamilton's eigencurve is defined as the, so there is an anti-equivalence between the analytic coherence sheaf on this T hat. T hat is isomorphic to GM cross GM, and so this is analytic coherence sheaf over this analytic space, and here you also have the, so you, let's say, you have this H-spheric, and you have, you take the image of this two endomorphism, this T-hat endomorphism of this sheaf. Let me write this E. Okay, so this is A. So this is the spec. Okay, and so this A is skinned over, in fact, over this T hat. And the Hamilton's eigencurve is defined just as you take the classical point, which classical point of finite slope, and you take the closure in this space. So for simplicity, it's the closure equal to closure. Maybe you can see here. So say is the closure of classical point of finite slope in A, spec A. And now this one you can just you localize to this C, goes to EC. And in fact, this one is generically free of rank 1. So this one is generically free of rank 1. Okay. So this is the Kato solar system over the eigencurve by this way. Now I have 2 minutes to tell you how to construct it. Now if you have a classical form of finite slope, and you can find a affinoid neighborhood of this F, and then you restrict this, say, Kato to universal to this V. Or now maybe your possibility will just write this, and this is element in, now we don't have this, and this. So this is a notation for simplicity, and you pass to local to QP. Then you have, and if you tend external coefficient to, so this is first this is a E plus function, and module you goes to R plus. R plus is the gamma. So R plus is the analytic function on the open disk, and this is bounded function on open disk, and you just replace by of the variable by the gamma. And we have isomorphism. So in for one form cases, this from Dana in family cases, maybe can I have 2 more minutes? Okay. This rho B is equal to 1. And in this case, we have triangulation for this Figa module. Triangulation in family of this Figa. So this is tensor this p-adic by phi equal to alpha theta and gamma equal to the weight, the chi-cyclotomy. Now you have a sub, and now you have element here, and you take look at in this p-adic. So this is free of rank 1, and you can take a base E. And here you can also take, here is also free of rank 1. You have this E theta base, and you wedge this, and is equal to a coefficient with respect to E. And this condition will tell you this element is not only in R, but also in R plus. And this gives you the two-variable p-adic function. Sorry for. So this element gives you two-variable p-adic function. So it's not only so it's you have this. So it's R plus the usual R plus tensor with this the global section of. No. It's heavily relied on the local global compatibility.
That's the key.
Yeah, it's very deeply so.
Suppose you take a CM elliptic curve, then put it in a family at weight 2. Then you have the two-variable p-adic L function. When you look at the whole thing over the trivializing extension, EP infinity, ZP cross ZP, over that you have a p-adic L function for this elliptic curve, two-variable p-adic L function. Yeah. On the other hand, just by deforming and looking at this, you have a two-variable p-adic L function for this family. How do the two compare?
You know. Yeah.
You're sort of the same.
No, if you really,
you should, I guess.
Yes, but if you want to precise every term, every factor, that's really difficult. Yeah, because here is, so if you remember at the beginning, I also have the operator RCD. We modify the algebraic diffusion into a measure. Yeah, we have that operator, and that is one point, and you also have to make choice of period. So in Kato, for one form, Kato really choose a specific period. And when you put in family, then we can't just take the period of Kato's period. It's also introduced some p-adic period. and I don't know how. I can't control it.
How does it compare with the
So there is a so
how
POTAS.
does it compare on the algebraic side?
So POTAS also have a theory for Samuel group. So using these Python modules in that way. So then I didn't follow the development, but I think Denis Benoit, he has something on this. Yeah, right? Mm-hmm. No, but this condition is from Hamilton's theorem of local global compatibility. So all the condition in our case is from the modular MOP representation comes from local global compatibility theorem. Kato don't use this.